Hello, everyone. This is Jamie Peterson of Wolfram U. It's my pleasure to welcome you to the new in Wolfram Language 13.3 webinar series. Today, we've invited Jon McLoone, Director of Technical Communication and Strategy with Wolfram Research Europe, to give us a comprehensive overview of the new and updated technology and functionality in Wolfram Language version 13.3. As Stephen Wolfram writes in his release announcement, there is now a whole subsystem in Wolfram language around LLMs and generative AI, but there are also performance improvements, mathematics milestones, and other enhancements with visualization, engineering modeling, the user interface, and more. I know Jon has a full 1 hour presentation to share with us. So I'll ask just one poll question now, asking who already has access to the latest version. So let me push out that poll to you now. Please provide an answer to that question. We appreciate it. You'll want to have access at least to a trial version of 13.3 if you want to try the examples in the webinar notebooks. So let me stop sharing my screen and I'll pass things over to Jon McLoone now for our overview presentation.
Thank you, Jamie. Okay, so I'm going to spend an hour going through quite a range of aspects of the new Mathematica 13.3. And I'm going to start by sharing a screen here so that we can see what we're talking about. And hopefully that's coming up now. As Jamie said, for a change, there is perhaps a bit of a theme that I'll center around with generative AI. And it's the standout, more exciting part of this release. But there are lots of things across a whole bunch of different areas, including performance and visualization improvements. I'm going to start from the interface and move kind of generally more specific as we go through the presentation. So if we start at the least specific, the thing that faces everyone, the user interface, we're always trying to make sure that the way that you can interact with the Wolfram language, and in particular in the Mathematica notebook environment, is as easy to use and friendly as possible. And this is one of the first places where the generative AI comes in helpful. So we've taken this sort of new technology that's been made available through people like ChatGPT and brought it into the notebook environment. So what do I mean by that? Well, let's bring up a chat-enabled notebook here. And the first thing is that just in the same way that before notebooks, you had the command line, which was you entered something and it was immutable. And then notebooks allowed you to review and change your inputs and keep a record that was reusable. That's what we're doing for chat. So if I ask some question and get it wrong, like what color is a degree, and ask it to answer that, we're getting a chat type response. But because it's in a notebook, I don't have to retype my question here. I can say, oh, I can fix that. I meant what color is a tiger, and get an answer. But in the world of the Mathematica user, probably while there are lots of uses of chat notebooks and personas and applications you can put large language models to, one of the most exciting from a Mathematica user interface point of view is that it now gives you a way for anyone to be a coder without having to code, either because it's quicker to do routine snippets of code, or because you don't know how to express yourself. You can now type in English in a much more general way. So let's do something like plot the moving average of the first 1,000 times into this notebook. And what it hopefully will do now is synthesize some Wolfram language code that will try and achieve the aim that I've described here. And if I accept that code, I like the look of it, I can plot it and see the result. And it's all contextual. So I could say, actually, I meant, I wanted the differences between the primes, which is in fact the example I intended to use, but forgot. Let's see if it can correct that. And it's taken what I've said earlier and given me some new code, which now has the differences. And so you can build up calculations step by step. You can change the style of the thing, and it knows the conversation that's gone before. So we've got this really friendly way of being able to interact with it. It also helps to explain problems better. So if I type in some bad input here, it's telling me here what this error means and giving me some suggestions on how I can improve that. And really, that's sort of as a coding assistant, it's really a leap forward from what we've been able to do in the past through natural language coding. Now, even if you know what you're doing coding, there's always room for trying to make the experience just slightly easier and slicker. One of those things that we've done in this release is to extend the autocomplete functionality, where you can type in some piece of a command name and get a match to things that starts that way, that's been around for a while, to support fuzzy matching. So if I'm thinking of list plot, all I need to do is type now LP and it spots list plot. So any kind of fragment or sequence of letters within the thing can match. Actually, that wasn't a great example, but time series model fit, for example, I just have to type a few letters like TSM and it tries to find suitable matches. So quick typing, and also if you don't know how a command starts, but you kind of know the kind of word that it might have in it, you can now get auto-completion to fix that for you. I put this one in because it might be one of the smallest user interface improvements around, but I personally make this mistake all the time, and so it's a very welcome addition. You're going to have to concentrate here as I type this one, that when you have a pure function in Mathematica, the ampersand marks the end of the function, but where does the function begin? Well, that's controlled by the precedences of which operators are stronger than which. If I type the ampersand now here, the pure function will very briefly, for a fraction of a second, light up to show me, and I'll do that again there, to show me the entire scope. So the option name, color function, has been bound into the function. So that's not actually what I wanted in this case. What I needed to do is to limit its application by putting in some brackets around here. And now you see when I type the ampersand, it's only the bit that I'm passing as the option that is a function, not the whole thing as a function. So that little visual hint, easily missed, but helpful in avoiding those kind of common scoping extent of the pure function uses. There's also notebooks are not the only way to code the Wolfram language. If you're writing kind of serious large-scale code or collaborating with a team, then you might be using IDEs like VS Code or Eclipse or IntelliJ. But there's also an in-between where we have a package editor that allows you to work on plain text packages in a notebook-light kind of structure, where you lose some of the typesetting and other fancy features, but you get to edit structured plain text nice and easily with things like line numbers added automatically. Well, that's been improved now with ability to search for definitions. So get node file seems to be a command in here. If I didn't know where to look for that, I can now type get node file, get node, and we automatically get the definition shows up in the search. And I can also, if I get one of those error messages that says mismatch bracket at line 402, well, now I can type in line numbers directly into that and say, let's jump directly to line 200 in the code and reach that without having to scroll through looking at the line numbers. Again, small features, but always pushing towards getting the maximum productivity and ease of use out of interacting with the language. Now, the user interface is something that needs ease of use from a developer point of view, but is also a way of deploying applications to users. So we also want to think about using the notebook system as a way of packaging up our work so that other people can use it without having to write code and get involved in the way that it works. And there's a few improvements here as well to be able to specify programmatic content more clearly. So one of those now is action menu, one of the many interactive notebook features that we've had for a while. Now it supports this idea of being able to give a nested tree structure to what's inside the action menu. So now within this, I can find submenus within that and submenus within submenus at some arbitrary level. So and when I get to the end, it'll do the action that's associated with that. Often we put in things that are useful as a paradigm for us to express issues to use, such as, for a long time, if you are in a working notebook and you misspell something, we underline the spelling error so that your eye is drawn to the error, and you can then it also has a mouse over effect so that you can fix the spelling mistake. But we don't like things where only we have access to them. So one of the minor features here is that we now have a paradigm, a symbolic way of specifying that squiggled underlying that we use for spell checking, so that you can now programmatically insert that any way you want around any structure within the notebook. So that just works within plots, within notebooks, anywhere that you can render contents. Squiggled is now supported. Another one that's a bit more subtle is we've had these various sort of highlighting things like framed and highlighted that allow you to programmatically draw attention to certain aspects of an expression. I think the very simple one here, I'm just saying anything that is an even number out of this list of random numbers I want to highlight. Now that's fine as output, and that's the way it's really been working for a long time. But the problem is when you have that as input, you don't want that to mean something. And that's why we've extended a whole bunch of these with strip on input, which means if I take that and now make it input and say, ask for something like the total of that, then that styling information is discarded. It's completely transparent to the evaluator now. Whereas in the old system, if I return that behavior by putting that back, then these things, that those highlighting have meaning, so we can only add up the numbers that weren't highlighted, and the rest we ended up with 5 unhighlighted zeros. Highlighted zeros, and so we can't simply multiply 5 by 0 here, because this thing is not a 0, it's a highlighted 0. So this ability to now make things so you can set up interfaces, say in courseware or in to highlight code, so that you can tell users, here's the bit you might want to edit by highlighting a bit of the code you want somebody to focus their attention on. That doesn't interfere with evaluation anymore with this new strip on input option. And for programmatically navigating around notebooks, either because you've got some action that you want to jump to a point in a notebook, or because you want to transform programmatically, such as building an index, we now have new mechanisms for being able to target and extract content based on things like the counter assignments. So this slightly cryptic bit of code here is saying I want to take the first part of each cell that I'm going to read from the notebook, and I only want the cells that are in the style of subsection, but are within the 4th title of this notebook, which happens to be, because I counted the slides before I started, we're on the 4th title in this slide. And so I'm able to pull out all of those subsections programmatically. So again, much more targeted ability to transform, extract, use notebooks as a mechanism for capturing data and then programmatic processing, and all of these things that you might want to apply programs to documents for. Okay, let's move away from the interface. We already saw the large language models in action within the chat notebook that we've created, doing things like conversational chat and being able to synthesize code to help us be productive as programmers. But there's a lot to bringing that large language model infrastructure into the Wolfram language just as another kind of computation. And there's various different levels of that. One is doing things purely like chat. So LLM synthesize is a mechanism to say, respond to this piece of input as if I've typed it into ChatGPT. So I've, in this case, posed a question to it, and I've got the string back that represents the answer. There's a few options and ways to control that, which we'll come to in a moment. Now, this, by default, LLM synthesize is completely a standalone. It's a stateless operation. So if I say LLM synthesize from now onwards, your name is Jeff, and then ask it what its name is, they're not, the two LLM synthesize commands are unrelated to each other. It's got a kind of infinite capacity for amnesia. If you want to actually have a chat interface, then we need a way of representing the history of chat. And so we have a symbolic representation of chat with this chat object. And so the idea is I'm going to start I haven't evaluated this already, so let's run this live. I'm going to start a chat conversation. And this object now represents a specific conversation. And I've started it in a particular persona. And now I can chat evaluate my input to the chat and get now the entire conversation back out. And so we've got my input and its output. And we can continue to do this so that we have a full symbolic representation of the conversation. This obviously would normally live behind an interface. You wouldn't access this in a code way the way I am here. you would have this behind some kind of HTML form or a form function in the Wolfram language. And probably we would want to do more than pure native chat as we are here. But this is the mechanism that automatically allows you to track that conversation and to be able to wind back conversations or maintain two separate conversations for two users at the same time, and all of these different things you need to manage through the symbolic chat. Now, I skipped over something there that I started with, which was LLM Prompt Bernardo. Well, what is this thing? This was a persona. And what it did, this particular persona is supposed to be a cool hipster kind of character that is a bit more hey there about its conversation. So it's just a linguistic style. But what technically this is reaching into a repository to fetch some prompt engineering. And the repository, like our existing repositories for code and demonstration and the like, is a website where there are collections of personas, functions, and modifiers that you can submit. At the moment, it's brand new, so it's mostly full of fairly whimsical illustration examples. So personas are things like speak like a pirate, or more useful things like speak in an expert tone, or speak in a reassuring tone, these kinds of sort of style things. The functions are things like take a piece of text and summarize it as a title. So title suggest is a more functional thing, and modifiers are things that that you overlay to change the results. So, for example, explain like I'm 5 is a modifier that you might say, I want to do a certain task, and then I want to modify the results of that task by saying put it in language appropriate for a 5-year-old. So we want this repository to grow with much richer things that might be 50 or 60 lines of prompt engineering to describe very complicated tasks. And when you figure those things out, it's an emerging field of prompt engineering, then you can now share that with other users and package it up so that you can use it yourself in a single named way. Now, another part of what we're doing, and a key thing for us, is that we want to bring together the strengths of large language models, which are fluency and being very human-like, together with the strengths of the computational world that we've been spending the last 35 years building out, which is reliability in computational thinking and reproducibility. So we want to join those two worlds together. And by way of an example here, here's a ChatGPT 3.5 conversation that I had through the ChatGPT interface, where I asked it something that I know we know about: provide data on livestock populations in Turkey. Here's its really fluent conversational essay that it's written. And I've highlighted two features out of it. One is the numbers, because LLMs are not good at numbers. They can't really do anything computationally thinking style, and they're not very good at remembering numbers because all numbers look kind of the same. But it's tried to convince me it's telling the truth with this citation. So I then went away and looked up the citation. In this case, it really did exist. Sometimes it makes up the citations. But when we drill into, after about 15 minutes, I found the right page in the Turkstat, Turkish statistical office data, and you can see the number was just made up. So it's sort of worse than wrong. It's wrong and trying to be convincingly wrong. So what we've, whoops, I don't think I want to close that. Do I have the example further down? So what we've added into ChatGPT is this plugin where, when I ask the same question after enabling the Wolfram plugin, you get this little used Wolfram box that appears. And if you expand that, you see that it calls Wolfram Alpha and says, hey, Wolfram Alpha, what's the answer to? And it simplifies the question down to something that we can parse. We send back some answer, and then it's woven that into the result. And then the second query, in the second time, it writes Wolfram language code, which we then use the Wolfram cloud to evaluate in a sandbox mode to, in this case, make a synthesize the code for bar chart of the data that came back from the previous query, and make a picture that then gets embedded into the GPT interface. Now, those two uses and that one plugin that we've made available to ChatGPT are already very useful, and they extend ChatGPT to be able to do things that are mathsy or computational thinking or data driven for the kinds of data we know about. But in a way, they're a nice advert for us, but they're not really the most useful thing. The most useful thing is to be able to make your own plugins, either into ChatGPT, for which we have a tool, or just at a code level, that achieve the same kind of result, but have access to your knowledge, your data, whatever it is that is not generally public to the world, And this is what that looks like from a language point of view. I set up a tool which has a name, and it's expecting a parameter which we'll call city. And then in this case, it's going to call the Wolfram Language City database population property. And you can give it some prompt engineering to help it understand how to use it. But already this is enough for it to figure out that with a name like City Population Finder, it can guess probably what that does. And now I use LLM Synthesize as I did before, but this time tell it, if you need help, there's a tool. And I say, use the tool to write a few sentences about Chicago. And it's invented some things out of its kind of fluency of saying Chicago's a bustling city, which I guess it is. But this number here, it achieved by calling the tool. It decided for itself that the tool would be useful. It called the Wolfram language and said, hey, what's the number here? And then it wove that into the result. And here's the same kind of thing plugged in through ChatGPT itself. Basically the same kind of idea. You've got an API function that does some, in this case, tax calculation, and then you make a plugin name, and there's a way of declaring to the ChatGPT interface the equivalent of LLM synthesized. Tell ChatGPT, if ever I ask anything about UK income tax, then call this Wolfram API in the Wolfram cloud, or could be in a private cloud, to compute this knowledge that I have injected into the system. And this API function could do anything. It could be some complicated mathematical operation instead of this trivial bit of arithmetic, or it could be a database connection and then some time series extrapolation from your sales figures that are private to you, whatever it is that you want it to do. But you can make that available behind the API so that the source is secret, but the knowledge is exposed to the LLM. Now, let's move on. There is also, as well as thinking about chat and injecting knowledge into chat, we can also think of LLMs as just a new way of achieving computation. And it doesn't have to be to do with chat. It's very powerful in things like unstructured data or data transformation. And there's a couple of ways we're exposing that. One is by being able to wrap some piece of prompting in a head that tells it this is going to behave like a function. So I can set that thing up. It doesn't do anything. It just declares this function. And my function is to convert the drug name to be provided into the purpose of the drug. And I have a bit of prompt engineering here that says return a single word. And now I can treat that just like a language in the Wolfram language. And in this case, I can say, take some database. My database only has 3 things in it this time, and map my purpose function over that to say, I've got these drugs, aspirin, warfarin, heparin, make a pie chart of how often they do different things. And it's found there's 1 analgesic and 2 anticoagulants in the list. Now, of course, without the LLM, which comes with all of this built-in knowledge, I'd have to build some kind of big dictionary that says aspirin has the following uses, warfarin has the following uses. And that would take lots of programming, which I effectively get for free by using the LLM. Another way that they're very useful is in kind of inferring things from examples. And here's our other main paradigm we've exposed in the 13.3 release, which is LLM example function. And the idea is you give it a few examples of what you mean, just like you might with a fresh employee, and say, okay, here's what I want you to do. If you see John is a 52-year-old male, I'm just going to update this because I had a birthday, who's 6 foot tall, I want you to write that up as a key value association in the Wolfram language. So here's the association syntax. I want the key to be name. And here's the name. I want the age to be in Wolfram language quantity representation. And I've given it a second example that says, here's a one where we didn't mention the person's age. So we want that to, here's an example of what to do in that case. And here's an example of 2 people mentioned in the same sentence. I want 2 separate associations. So I've given 3 examples. And again, I've got a function that I can just now apply to unseen data. So I could map this down some unstructured data that I've got in some database and say, okay, I want you to turn that into a computable data set. And it's able to turn that into a data set object where we've got name, age, and height columns appropriately marked up and ready to be computed with. And it turns out this is a really general piece of functionality that you can give all kinds of example-driven things. So this isn't doing an extraction, this is doing a transformation. I'm telling it roughly what we want it to do, which is to fix transcription errors in a speech-to-text system. Here's an example. We're talking about hearts, and you've got a tastemaker. That was probably a mistranscription of pacemaker. I've got 2 examples, and now already it's learned enough to take, I have cats in a glad aroma in the topic of eyes, and figure out that probably means cataracts and glaucoma. Really powerful functionality. And we're trying to be agnostic. These things are all called LLM synthesized because we want to be able to support many backends. So there's a configuration option to be able to say which LLM you want to use. At the moment, basically all you can do is to use that to control whether using GPT 3.5 or 4, and whether you want it to be very creative or less creative. But that will be a mechanism to be able to say I want to switch to Bard or Bing or some local LLM in future. Right, let's spend a lot of time talking about these first things, so I'm going to have to speed up a little. Of course, there's areas we've been working on for years that continue to be developed. So machine learning has faster neural networks. So just fundamentally, the execution of neural networks has been optimized. So for example, the experiments I did with the Wolfram image identifier net is about twice as fast as it was before. So anything you're doing in neural networks will just benefit without you having to change anything. It will just be faster. We've got a whole collection of new neural networks for doing new tasks, like there's a portrait generator task, there's a vision recognizer that allows you to understand better what features of the image are important. There's some medical image transformation networks, some new segmentation, and we've got this pose estimation that allows you to figure out how people are standing in a picture. And there's another one here, which is a multi-domain, that's being able to take both text and images as input. There's new image identification models, and so now you have a choice of methods of whether you want better or faster compared to the previous image identification networks we had built in, and better integration for things like external MXNet-based models, and some nice syntactic sugar, so that all of the tools you can apply to neural networks now can also be applied to traditional classical model fitting, like nonlinear model fit. It takes the same syntax. You can use the same performance measurements tools on it now, just by improving the language design. Okay, another general thing that affects everyone is visualization. We've got a significant new direction that we started that is not profound, but is still nevertheless important. For a long time, we've had really powerful visual interactivity. So we could make manipulates where you could slide sliders, and the whole contents of the plot would recompute, which is very nice. But it missed out on the other end of interactivity, which is superficial cosmetic interactivity, which we're now filling in, that is trying to make things interactive with zero effort on your part or minimal effort. So the idea is now that if you have anything that is a line style plot, of which plot is one example, now when you mouse over it, it automatically has some level of superficial interactivity. In this case, the nearest point gets highlighted and I get the coordinates of the point without me having to say anything. But of course, typical Wolfram style, we've said, well, what are all the ways that you might typically want to highlight interactivity with plot highlighting? So there's an option to control the style. I might, for example, only want the Y value or the X value, or I might want to see that point on the axes at the same time. So there's a drop line style that allows me to, and of course it works over multiple lines as well. So this is showing me the point and the drop line. If you've got multiple points, you might want them to be independent like this, where we're only interested in the one we're mousing over, or you might want to consider them together. So there's a X slice option that will slice through all of the lines simultaneously, a Y slice version that slices through all the lines horizontally. There's a kind of call out version. There's a version for handling different styles for different lines, so that we can highlight when there's a lot of plots going on, what are all the points that are on this particular trace within the plot. There is the ability to specify them individually. So here I've got a ball with drop lines, and this one I've got a ball with values, so they don't have to all be the same. And there is also programmatic control, so I can specify not to be mouse driven, but to be set to a particular value. So I can, if I'm printing this in a book, I might want to just highlight the important point by saying placed at X equals 6. And that also, of course, allows us to do things like animations. So I can programmatically change that value to make things like movies that, in this case, slowly slice through the different values of X for this vertical drop line. So in a way, they're superficial, But when you want to get your points across in a presentation or have people understand your plots, this level of kind of interactivity and automatic highlighting is actually quite powerful for understanding and really just looking professional and nice. Similarly, we've been adding for a while different ways of being able to get really fine detailed control over how to draw your user's eye in really professional visualizations. So we've had ways to emphasize and de-emphasize contents with drop shadow for emphasizing and blurring to de-emphasize. And there's one more to add to this world now, which is haloing, which allows us to take some piece of contents and put a glowing halo around the thing. So this is a primitive that says everything that comes after this point until cancelled is going to have this outline halo, in this case in magenta style to 12 points. But here's the sort of more practical purpose of it, is that you might have a map, and there's a whole there's some features you want to draw attention to. Well, we can just say halo that particular polygon of the United States, so that it kind of pops out of the page with greater emphasis. So this sort of nice kind of glow around the thing just draws the eye more than simply having the colored polygon. And some things that we're just always trying to get right, that since we last updated color functions in the Wolfram language, the typical quality of monitors has improved. And so there's been a little tweak here to go from the default color scheme on the left to the default color scheme on the right, because we can now rely on a greater dynamic range of the typical person's monitor on screen. So the darks are darker and the lights are lighter without having to worry about them being lost in shadows or bleaching out, as we had to worry when these color schemes were first set up. So even these kind of trivial things get reconsidered and reviewed periodically for maximum impact. Did I skip a section there? Visualization, no programming. Okay, so let's get on to another very general thing, programming. Everyone has to program if you're going to do anything serious in the Wolfram language. Quite a lot of our effort here has been working on performance. There's a range of things going on in this space. There is a new mechanism for structured matrices. So when you have arrays that have particular structures to them, they're often very efficient, both in memory and computation time ways of representing them. Here's the most trivial example I could think of, that I've got a 30 million by 30 million identity matrix, and I'm multiplying it, I'm doing the dot product with another 30 million by 30 million identity matrix. In dense form, that would be 900 million calculations. It would take a lot of memory, a lot of time, but being able to hold this symbolically, it takes essentially no memory and no time to do that computation. Obviously, that's a very trivial example, but having this idea across these range of different types, and a lot of the operations in matrices can now say the target structure you want to achieve. So I could do that same thing, but say, okay, I want the target structure to be sparse. Now I have to hold 30 million values down the diagonal, or I could say dense, in which case it has to hold all of those 900 billion values, 900 trillion values, I guess. So a lot more control over managing minimizing the amount of memory, being able to use the algorithms that support these structures directly and getting things done faster in less memory. Another key part of performance is the data structure object. So if you are worried about performance and you have some kind of knowledge of computer science data structures, then you really should know about this. The idea is that where lists and associations are very general in the Wolfram language, you can put anything in them. I can have a list that contains numbers or strings, or numbers and strings and neural networks and images and everything. If you are willing to give up that generality of the kinds of things you can put in and the kinds of operations you can do, then there are much more efficient ways to store that data. And so the data structure supports a collection of these. We've added a couple of new ones, and new operations on a couple of the built-in ones. So this is one of the new ones, a cuckoo filter, which allows me to set up a list of numbers and then ask questions like, could it contain the number 1? So it's not a guaranteed, it's it is guarantees if it can't, but if it might, it doesn't prove there's a 1 in there, but there's a good chance there is a 1 in there. And I can do that much, much faster than doing the same kind of operation with member queue, in the Wolfram language. You can see here that the time taken has been about 100 times faster. And this is just a general thing we've been building out. There's about 20 of these data structures now. Performance is the sole reason to go there. Now, this all sits off the back of the compiler, which is this long-term project we have to allow us to take the flexibility and power of the Wolfram language, but then to be able to, without rewriting code, to be able to declare types and optimize that code and convert it into machine code to run locally on a computer. So you get the performance of C or these sort of purpose-built performance languages like Julia, but with all of the knowledge and infrastructure and power and elegance of the language of the Wolfram language. One big breakthrough that we've achieved now is the step where you compile the code that you do up front, that you have to invest some time in before you get the fast version of the code. That is now much faster. And we've achieved that because we've now compiled the compiler. So we've pointed this compiler technology back at the Wolfram language code that was used to write the compiler to make the fast version of compilation. And it's also a testament to the fact that the compiler is now reaching a level of maturity that really quite large code projects like compiler can now be compiled. For those of you who have external DLLs and libraries you want to use, there is now a function interface within the compiler, so you can directly connect to DLLs without having to write any bridging code, including things like passing raw memory around if you are down in the trenches of coding. And we also want compiled code to work nicely with Wolfram language that still can't be compiled. Even as we grow the number of functions that are compilable, there will be for a long time functions that can't be compiled. And now we have this ability to tell the compiler that when it has things that we know can't be compiled, that it optimally will call back to the Wolfram kernel to be able to achieve that. So here I'm declaring a very simple function to be compiled that is a number plus the area I of a number, but I can tell it there's no chance you're going to be able to compile area I, call the Wolfram kernel to achieve that with kernel evaluate. But I'm giving it some extra information that says, given we've got a real 64 in, I believe we'll get a real 64 back. And that allows it to really optimize that compiled code to make something that is now machine code executable, but calls back when needed. So you don't have to make this, am I writing code for the compiler or am I writing code that will evaluate in the kernel? You can now sit in both camps simultaneously and incrementally extends compilation coverage as we incrementally improve the compiler over future versions. And there's some new compiler types as well. So there are more types that you can declare to the compiler. Now, while most of that work is about performance, we also want to make coding easier. And there's a couple of things that are fairly minor, but are nice nevertheless, that there is now a symbolic representation of unit tests. So we've had the ability to make unit tests and run unit tests in the Wolfram language for a while, but now they can be programmatically transformed and created. So here's the basic syntax. We create a test that says the operation 2 + 2 should return 4, and now we can run that test and we get a tick to say, yep, the test passed. So if I've broken plus or broken the number 2, then that test would fail. Obviously, you would write tests to test your own code, not the built-in functions. But because these things are programmatic and we can programmatically analyze that and see, well, how did that test perform? I can write my own scripts that, for example, take a big collection of tests and say, okay, I want to pull out only the tests that test the plus function. Now, before tests lived in notebooks, I lived in files, so you kind of had to run the whole test, or you had to make a different test suite for a different purpose. But now you can build large libraries of tests, but not have to run them all. If I've changed my function, I might only want to run tests that involve my function, because there's no point running all of them at great expense if I know I haven't touched the code for the rest, for example. Or I might only be interested in analyzing the results to say, of all the tests, I want to get the slowest test, or the test that slowed down the most, or I can programmatically analyze the results and all of that, because there's a way to represent these things in the Wolfram language. And likewise, there's a way to represent remote kernels now. So if you're doing things like parallel evaluation with the parallel programming tools, it's now programmatically controllable to say, switch the evaluator to be the big cluster that I'm allowed to use for 1 hour today, if it's between 9 and 10 in the morning, but if it's other hours, automatically run it on some kernels that are running on my machine. So I can programmatically control these things and manage them much easier than before. Right, let's get a little bit more specialist now. So let's talk about some maths, which of course has been at the heart of the Wolfram Language and Mathematica since the beginning. One of the things that we have excelled at is support of special functions, these things that have emerged from particular mathematical or physics problems and effectively encapsulate a whole bunch of knowledge about, say, the way waves behave. We've got the largest collection of special functions in the world, and they've got more and more general with things like hypergeometric functions that are generalized, these sort of narrow things like Bessel functions. And we've now kind of reached the end of that journey, or almost the end of that journey, by having these super general Apple functions that that generalize the other special functions for multiple arguments. So these 4 new functions kind of are now at the top of knowledge of special functions. Of course, if you're in maths or physics, you might care about them in their own right, but a lot of what we want to do is to power other functionality. And one breakthrough we've reached now is being able to use all of that knowledge on special functions to do things like this inverse Laplace transform, which, while you might not care about the properties of the Whittaker M function, the fact that we can take this relatively simple expression and now find the Laplace transform and solve the engineering problem that it represents in a closed form is made possible by this great knowledge on special functions. And we can work with this expression because we know things like the series expansion and the derivative and the integral of these special functions. And now, if you look at the textbooks on the integral transforms of special functions, we've pretty much covered the known knowledge that there is in the textbooks, that all of the reference textbooks we're looking at, we can solve all of the problems. And I did hear rumors that we discovered a couple of mistakes in textbooks because we're now doing it programmatically and can systematically check their results. Another area that is not new, but we continue to extend, is interval evaluation. So where you have a worst case scenario for an uncertain number, we've now extended that over lots of special functions. So for example, I can take this Carlson RF function and say, I don't know what the second argument is. It's about 2 plus or minus 0.2, and the third argument is 3 plus or minus 0.1. Well, now I know that the result is centered 0.72 and is no worse than plus or minus 0.0229. And likewise, ordering of special functions, ordering of these intervals is now also computable. So we have the kind of calculus of when can you say that something is definitely bigger than something else when there is uncertainty involved is now computed. Now, calculus is an area that we've excelled in for a long time. You would think that there's not much new to add, but in this case, what we've added is principally repackaging the engineering that we've done to new problems in a more elegant way. So these are not problems you couldn't solve before, but we have now the notion of line and surface integrals that stop you having to transform problems to represent and use any geometry within our geometry system. So this is a trivial example to say, what's the integral of x, where in the plane where x and y are elements of a circle and they all cancel out. But if I integrated this function 1 over that, we get the length of that circle circumference. But making this work over anything you can express geometrically, and including compound things like geometry unions or intersections, and to do that over 3D and surfaces is quite powerful to just package that up in terms of a function like a line integral. Here's a slightly more interesting example. Here's perhaps a magnetic field or a flux field, so a vector field in 3-dimensional space, and I've got a region that's going to intersect that. So maybe I've got a sheet of metal that is going to pass through that vector field. What is the flux that particular surface will cross through? Well, that's simply the surface integral of the function that was the vector field over the region that's defined by the parameterized formula, and we can get the answer just straight out of that by saying surface integrated and get a closed form solution. So you could do that before, but there was all kinds of transformation work that you had to do and change of variables and all of that kind of nonsense that made it hard work. and also some kind of robustness and performance improvements. So, for example, RSolve is generally twice as fast over a large collection of classes of problems, such as this one. I'm going to skip through over this one, other than to say that we have now a proper representation of finite fields, because if you return for next week's deep dive into the computational and math side of what's new in 13.3, you'll get to hear this in great detail. But the basic idea is we now have a symbolic representation of finite fields that looks like this, and we can do operations like multiplying elements from that finite field, and it does the right thing, or factoring polynomials over finite fields. And this is a very powerful framework for finite fields that we've largely rolled out, but more will come in version 14. But you can hear about that if you return next week. Another area in the math space is we have geometry we've been working on for a long time. And of course, indirectly, I've already been using that in this talk with that circle that I integrated over is something out of our geometry framework. But there's still more that we're building into geometry. One is to deal with descriptions of regions and distances between them. And that's the main addition here. So we now have, we had region distance as a function before, but region distance before supported only a point and a region. So you could find the distance from a fixed point to the nearest point on that region. Now we can find the distance, the nearest distance between any two regions. Obviously, don't have to be circular. They could be any region you can describe with the framework. And there are also different interpretations. There is region Hausdorff's distance, which is well, let's do region furthest distance first of all, which is the furthest point within two regions, so the worst to the worst, whereas region distance is the nearest to the nearest. And region Hausdorff's distance is the nearest to the furthest. So it's the maximum of the minimums. Or is it the minimum of the maximums? It's one way around or the other way. I always have to look up the definition to be sure. And we also want to extend that idea to collections of points that describe regions. And so we have some new ways to describe a collection of points. And you can think of these as being the kind of robust and unrobust versions, like the mean and the median. Circumscribed ball is the smallest circle or ball, depending on your dimensionality, that includes all of the points. So the minimum enclosing circle, or a minimum enclosing line, or minimum enclosing ball. That's not very robust to outliers. You can imagine if one point was way off in the distance, the ball would suddenly become huge, but that doesn't really represent the point. So in the same way that you have a median for finding the center versus mean, we have inscribed ball, which is a more robust version that's less immune to outliers, and that finds the convex hull of the points and then finds the largest ball that fits within the convex hull. So it's another way of basically summarizing roughly what's the spread of this collection of points as a geometry, which then you could use within all of the framework that uses geometry, such as region distances or integrating or so on. We've also got a collection of new formats. Mainly they center around AR type formats. And there's a nice utility function to sit on top of that allows us to take anything in the 3D geometry and say, AR publish that. What that does is it basically exports to an AR format and then wraps it in a cloud object with some metadata to declare what it is. And you can then point a modern mobile phone at this QR code and you get augmented reality, where you can now walk around the object in your real world. So the book here is in the real world. We're looking through the screen of the phone, and as we walk around, the object changes as if we were looking at it in an augmented reality world. I've thrown it into this group, but SVG import I think is actually quite an important one as well, and I've already made use of it. This is scalable vector graphics, kind of one of the standard ways to publish graphics on the web that don't get pixelated when you enlarge them. We've had SVG export for a long time. Now we can do SVG import to capture SVG images into the lines and polygons or filled Bezier curves or whatever they're represented as within the Wolfram language, and then transform them or compute with them or show them on top of something else or whatever you want to do with them. And I've put it here as a small print, but actually I think this is pretty profound. There are some really, depending on the complexity of the problem, some dramatic performance improvements in a whole collection of the core infrastructure functions of geometry. And for those of you who work in this space heavily, you'll know that there are some robustness problems in 13.2 and earlier, where the memory usage grows dramatically, or you get problems that simply fail because they're beyond the scope of the functions, even though they seem like they ought to work. So these are no new functionality, but they are really quite a lot more powerful before they start saying I can't do that, and also quite a lot faster, for particularly when you have complex geometries with lots of meshes, for example, can get very complex very fast. Another field, of course, starting to get more and more specific now, is we've got lots of tools for programmatic audio and video processing and creation. So let's talk about generation first of all. Here, the whole world of generative AI comes in. Image synthesizer has been added, and image synthesizer has a whole collection of uses. One is to be able to just generally make up illustration images or test images according to a language description. So this isn't a search or anything. I have described the image, and what I get is then generated programmatically. So if I said a tiger smoking a cigar, I actually rehearsed this example, so we'll see what we get. I don't know whether it'll do a decent job here. We can now generate via an OpenAI-backed service here, hopefully a picture of a tiger smoking a cigar. Hopefully should only take a few seconds. There we go, a tiger smoking a cigar. And perhaps if I'd added photorealistic, it would have made it look more like a photograph instead of a cartoon. We can generate multiple versions. Oh, sorry, and this is a different form of that. We can take any image, it knows nothing about the prompt now, and say, make variations on an image. So, for example, if I did an image, let's grab from my webcam here, me, I can't remember the keystroke on Windows. Let's grab that image here on the webcam and paste that in. What we'll get is 3 synthesized versions of that image, not necessarily looking like me. It's going to try and capture the essence of that picture. So it's probably going to be a man in a blue shirt wearing glasses and sitting in front of a bookshelf. So here's 3 synthesized versions of that source image. And you can also use it with masks. So for example, I can take this holiday photo and I can say I want the McLoone family removed from the image by telling it to crop out that part of it and synthesize a piazza that fills in that space. So we've got image infilling. We can describe what we want in that infilling, and it's I say put a statue in that space, and it's made one up. And we can also use that idea to image extrapolate. So here's a picture of me at home writing this talk, but it's imagined the room around here. I've asked it to infill outwards. And so the fact that, in fact, there are no windows on the right-hand side of my room, it's just imagined that because there are windows on the left-hand side of my room. And it's imagined that I must be standing at a desk because it can't see what's going on. Oh, and you can also describe the contents of the outfilling as well. So I added man listening to monkeys here, and that controlled its outfilling. There's better speech synthesis through external services. So there are services from Google that generate much more natural speech than our built-in speech synthesis. So you can call that from within the language. Things like the tour video now understand geographics, so we can give backgrounds in the contents in terms of geographics or computer geographics, and we can control the path that we tour so that it understands things like the coordinates within geospace. So here is a zoom of a map from Munich to Würzburg. And again, all the way through the system, we're trying to find ways to speed things up. So this video trim example is, when I measured it, at least on my personal machine, was about 5 times faster. So the fact that we have to scrub through 89 seconds of video out of the 90 in order to trim 1 second was done relatively inefficiently in the past. And now we can get through that quite quickly without having to scrub through every frame of the video, reconstructing all 89 of the 90 seconds. Now that's on the generation side, but we also want to do things programmatically with video. And very often we're trying to measure things or transform the images. So one of those things is we've extended shape detection. So we've had infinite line detection within the Wolfram language for a while, but now we can also find line segments, circles, and ellipses. So here's an image where I'm going to edge detect this picture of an eye to highlight the boundaries. And now I want to find within that circles, and I'm going to find the biggest circle. And it's found the biggest circle. And if we overlay that here, you can see that we've identified the iris accurately from the image by being able to target circles within the image. Another thing that we've had for a while is image saliency filter. And the idea of image saliency filter is, where would the eye be drawn to in this image? We've now got a new neural network backed mechanism for this, so I can do that. The old image saliency filter really worked on a pixel by pixel basis. So you would have got a whole bunch of features around the sign, but you would have also got the odd dot around the tops of trees and things like that. This works really more on a whole holistic level. What region of the image is my eye going to be drawn to? And it's picked out the sign that says that's probably what you're going to see. So if you wanted to, for example, crop that and infill it, you could target that automatically for infilling. And we're also always looking for ways in which we can use these kind of bits of functionality within other functionality. So another function that's existed for a while, remove background, which was really intended for things like removing a green background or removing a background that was out of focus. We have those kind of mechanisms. We can now use this saliency measure as a way of saying, keep only the bits that your eye will be drawn to. So it's decided we would look at the tiger, we wouldn't look at the boring background, and so I've used that to remove boring background, ready for infilling or to target the training or whatever we're doing with this image. And also, we're always looking at the interactivity with these things. So there is a reworking of the GUI for audio now to be more consistent with the video GUI. So that's things like being able to control which speaker it's going to play on, the appearance. So that's the medium-sized appearance, but I could set that to a detailed appearance or minimal appearance. So a variety of these different interface controls. There's just now easier to make nice interfaces where you let the user control the playback of audio. Okay, we are running out of time, and fortunately, I think I'm on to my last section. Obviously, lots of what I've been showing so far is useful in engineering. I've labeled this section really because these things are only really for engineering. And there's a couple of new areas within this space. One of those is that we have a whole bunch of non-Wolfram language technology for building system models. And so this is the Wolfram System Modeler, where you can draw, for example, circuit diagrams. So this has been created in System Modeler. I've drawn a resistor and an inductor and a motor component. And then I've got some physical components I've dragged on, which is something with momentum and so on, and some kind of sensor on the end of it. So I can then declare that as components and drag that component into my design for a car or whatever I'm building. So System Modeler is great for building these hierarchical models and simulating specific components, like what happens for these sets of parameters. But we want to integrate that with the whole computational world of the Wolfram language to be able to do things like optimization and simulation and machine learning and all of these things as well. So one of the things here that we're doing to integrate is to bring the whole optimization and machinery of gradient descent that's used for machine learning and bring it to bear for system models. So I take this model and I've got some data I've observed in the real world, and I can plot the two together. They're not very good. Why is that? Well, it might be that this, of course, isn't the model, that I've forgotten that there's something else controlling this wheel, that there's another, there's some kind of second motor that's pushing it another way, and I haven't built the right model. But one possibility is that I simply haven't got the parameters right. I don't know how heavy this inertia component is, or I don't know the voltage that is being fed into the system. So the idea is that I can now calibrate that model in the same way that you would do fine minimum or you would do nonlinear model fit. I want to find the values for the resistor and the spring damper that will improve the model. And I'm going to allow it, and I want it to go through the different inertia settings and tweak these values until it gets a better model. And what we get back is a new version of the model that is now calibrated with new values for the resistor and new values for the damper. Now I can plot that over inertia, and you can see that it's now a much better fit. That was the explanation for the poor model performance. So we're bringing together best of both worlds, model building and model testing, together with the whole computational analysis and optimization world of the Wolfram language. Another one that is in a different field, but still very much engineering, is the whole PDE solving system that we've been building out, has some new capabilities. The key thing here being Yo hyperelastic properties, and there's another property measurement that are the way that certain materials stretch under strain and stress. And so this opens up classes of problems where the materials have Yo hyperelasticity. So imagine this is a rubber membrane, and I want to grab hold of it with clamps attached to the red and green area and pull on those. How will it perform? So depending on the material, it performs differently. With a Yo hyperelastic material, we can now model that, and we can see, for example, as I pull on those, how will the material deform, and what's the stress and strain at each point at a given time. So this material properties has been an ongoing thing for us to be able to, more accurately model real world things that you might be able to simulate or optimize. So I'm out of time, spot on the hour that I told Jamie I would take. So there's a bunch of things that I haven't bothered to talk about, lots of new documentation, dates have been made more consistent, astronomy is more accurate, and some things I considered too boring or too complicated to describe that maybe will be covered in the next couple of weeks webinars as they dive in deeper to some of these sections I've glossed over, and I would encourage you to return. But to summarize, the exciting things that are kind of completely new areas are all forms of generative AI, large language models, generative images, being able to control those for chat or control those for custom chat with plugins, or using them just as another kind of computation. We got a lot of performance improvements, both in cross coding and a lot of the computation. And I think the visualizations are really nice just for making things more attractive, more professional, and more impressive. Plus a whole bunch of specialist things that obviously I've been walking through. So I can see there are some questions waiting for me to take. I'll turn my attention to those now. So now would be a great time to ask questions if you haven't already. Type them into the Q&A window at the side of the screen, and I will try and get to those. Okay, so Mohammed has asked, is FE backtick evaluate generate enough that wrapping it around anything will evaluate it in the front end? No, so the front end knows how to evaluate certain things. Oh, thank you, Jamie. Yeah, it knows how to evaluate certain things, but it's really quite a minimal set. So we've put in things that we need to make certain things efficient, like the front end knows how to add numbers, so that if you want to set the option to something to be dynamic of window margins added together to figure out the size of the window or something, then you can compute those things. And it knows a few basic operations. Some of the things like notebook find, the front end knows about, so you don't have to call the kernel to tell the front end that it wants to find something. But they are a somewhat minimal subset. It is one of the longer term ambitions that as the compiler is capable of generating more compiled code, we may be able to take more Wolfram language functionality and compile it and inject it into the front end as compiled code. And that might be a route to growing more, but that's not one of the priority outputs at the moment. Okay, so I'm not going to take your other question, Mohammed. I'll take a look at that later, since it requires me reading a Stack Exchange post. So let me go on to John's question and see if I can take that. So yeah, so do I have to something special to make my C++ compiler work? There is some declaration of the external compiler. I use a Mac myself, and so I just have to make sure I've installed and I forget what it's called, the Apple's development environment onto my machine as well, Code Tools or something that makes the compiler available. But yes, there are some details in there where you can decide which compiler to use. But the mechanism that it does compilation these days is via LLVM. So it does a conversion to LLVM and then converts that using the LLVM compilation. So it may be that for compilation of our code, you don't need to touch those details, but if you're calling back into something that you built yourself, you will need to get involved in the details. There is lots of new documentation on the compiler, so I would encourage you to look at that. Do you have inscribe square or inscribe X? There is bounding box, so you can find the for points. There is a mechanism for bounding boxes, and I believe rotated bounding boxes. So that's a rectangle that is not necessarily X and Y perpendicular. And you can also do bounding boxes for ellipses that are also, again, not necessarily X and Y bound in their semi-axis, but rotated ellipses. They actually aren't in that geometry functionality. They are, I think, in, I will have to look up the functionality. They are in component measurements. I know you can get them from that. So you might have to do a weird loop through images. Perhaps a resource function that should be written to do that. Does image synthesize use OpenAI's painting model? It does. So the back end of image synthesize at the moment is entirely the OpenAI model. So it's just a services call to OpenAI. So we don't have, for example, the diffusion approach where yet for image synthesize, where you could, put a circle and a green rectangle on the box and then say to it, turn those into a sunrise over a grassy field and have it modify. That model isn't supported. So the models we have at the moment are text to image with a mask and image to image. Those are the models that we have. And it's worth pointing out the mask is, while only the bit within the masked area is generated, let's go back to this example for a moment, then you will see that the area where the mask ends always joins up pretty much perfectly. So you can kind of see there's a slight texture change, but there's no kind of glitch at that point because it's contextually aware outside of the mask to blend it, but you can't. It is only updating the inside of the mask, and it's on all or nothing. You can't partially mask this and have it partially updated. It's you are simply saying where can and can't be used. Interesting little side observation, actually, that when I wrote this example, I originally clipped out the people from the source image, and I left the shadow. Because of its contextual awareness, I couldn't get it to infill with an empty piazza because it saw the shadow, knew the shadow had to be explained by something, and so it would always stick something in the area in the image to explain the shadow. So there was always a statue or a person invented. So it is contextually aware, but it won't update outside of the bounding box. Right, next. Yeah, so comment from Sid employing support for GPU architecture on Apple. I give that a thumbs up too, and I've certainly lobbied for it. I believe there is some hope of that, but it was most of the GPU stuff that we're doing, of course, is for MXNet, and MXNet head branch wasn't supporting Apple, and it was too big a project for us to take on. But I think there is some hope that MXNet itself will support Apple GPUs. And one of the targets for the compiler project, which we haven't reached yet, will be GPU support. So being able to write Wolfram language code and generate GPU code. And I would certainly hope that that will include Apple as a target. But yeah, I've given a thumbs up internally to that one as well. When will, yes, okay. So lots of lobbying going on here. When will write to database capabilities come to entity framework for relational databases? The answer is I don't know, but actually, so the idea is that the entity framework where we talk about our built-in things, and you can say, give me an entity that represents all of the countries that are also both in the EU and also in the G8, and then execute that. Some sort of symbolic representations of queries. For searching from databases, those can be compiled automatically to SQL and generate an optimized database query, but you can't use them for writing. I believe it's been implemented. I believe that it is waiting on a design review and quality assurance, but it was not scheduled for 13.3, and I still don't know if it's on the version 14 schedule list. So it's coming, but it's a priority question to get it finished. It will come at some point, I'm sure, because lots of work has been done on it. So also need SQL window function in Entity Framework. Yeah, you can use the window function if you go back to database link, but I don't have anything to say on whether it's coming to the Entity Framework. I certainly have not seen any work on that, so I would not hold my breath on that one being in the next release, I'm afraid. Sorry, long question. Let me just see if I can take this. Okay, so there's a question here about language support of languages. So, my understanding basically of the way this has been done is that there is a single language model that has been trained on all of the world's text. So while one could imagine making a fine-tuned thing that is very optimized for particular languages, when I do something like, let's go back to text synthesizer, let's do text synthesize. So I ought to be able to do here, and I can't remember whether this is the syntax, LLM prompt translate comma, I'm going to do something I stand a chance of seeing if it's done the right thing. Let's do French here. What I'm doing here is just setting up the prompt engineering to answer that question with the modifier that I want it translated to French. Okay, so actually I've done this it's set this up as a translate the following phrase to French. So it's done the expliquer en trois noir on, so explain a whole black in 30 words is translated. So this is because the same model that I'm calling knows umpteen different languages. Now, we might have some trouble rendering some of these things. So if I do something like Japanese, I think we're going to be okay. But if I do something like Arabic, because we don't have correct right to left translation, the string is correct here, but our display of the string is incorrect. It actually should look, I don't know if we've got any Arab speakers here, but string reverse of that is a bit closer to what it should look like, but Arabic is got particular issues with letters joining up that mean this still doesn't look quite right. But yeah, it's all one model in the background that we're using there. Is there a good book for using machine learning besides the Wolfram documentation? I can't give a straight answer to this, but I have heard good things, and I have an intention to read Etienne. Is it Etienne's introduction to machine learning with the Wolfram language? I think if you search it on the Wolfram website, you'll find some promotion of it, and it's a full explanation of the process of machine learning that happens to be illustrated with the Wolfram language machine learning framework, more than the documentation, which is principally focused on how to use the framework. I understand it's a good primer for learning all about neural networks, but I can't actually say that for sure because I haven't got around to reading it yet. It's on my to-do list. Right, what else we got? Any work to bring proof assistance into Mathematica? There is already a proof assistant. Find equational proof is the function. If I open the help on that, you will find that you can give it a statement and an axiom system, and then it generates quite a complicated object that you then either need to turn into a notebook or turn into a series of steps. And and it can work with much more complicated axiom systems. So somewhere here there is in the applications. I think this is Stephen's preferred example because I think this is his one-line axiom system for. Is that his one-line axiom system for Boolean logic? No, I don't think it is. But anyway, okay, this is a Boolean proof that is much more complicated. You can see the proof structure is quite big. So there's no active work on that at the moment, but this is already quite a powerful function. And there is a utility function whose name I can't remember, but might be in the C alsos, which is axiomatic theory that allows you to, is basically one of these data objects that lets you look up the axioms for particular branches of mathematics, ready for that function to be able to use without you having to specify all of that by hand. I don't know about FBX import, Raina, so we'll get back to you on that if somebody can add that to our follow-up things to look up. Okay, as long as we're lobbying, split windows would be great. I too would like split windows, but I think the front-end group has a number of higher priority projects, so I haven't even tried lobbying that one myself. There are some other projects that will push up the agenda, so at some point I suspect it will happen, but I'm afraid it won't be this year. And the others are thank you. So I think I'm out of questions that I'm able to take at this moment. I might take a quick look at this Stack Exchange post here to see if I can understand what Mohammed's question is.
Thanks, John. Fantastic job. We got through so many questions, and thanks also to our behind the scenes staff who have been working to submit those responses. John, is it okay if we wrap up, or was there something else you
Yeah,
wanted
so
to?
the last question was about netlink, and I don't know anything about netlink. I used it once to try and do some Excel things from Mathematica, but I'm afraid I have no knowledge of how it really works. I was copying and pasting code I stole from elsewhere.
Okay, well, we have a short list of things to follow up, and we will do so after the webinar. So thanks everyone for those great questions, and we appreciate everyone's participation. We'll see you next week. Thanks, John.
Thank you very much, and goodbye, everyone.